Hello everyone, it's Olli here again. In this video I am going to show you my camera array tool for Blender and go through its all latest update features. So let's dive in.
Activate.
Okay, so even if you haven't used this Blender add-on before, I will show you the basic idea how it works and for what it can be used for. And in the same time I will also show you the new features which have been added to it on this major update. Just like in the real world, we have these complex and quite expensive camera rigs that can capture real-world objects or characters and use these images to create 3D models or even volumetric videos. The basic idea behind the camera array tool is that it allows you to create a similar camera array studio virtually inside Blender and produce a synthetic image datasets that can then be used for things like Gaussian Splatting conversions. The setups where this can be used are primarily object-centric usage, which means setups where we try to capture individual things, such as characters or other single objects. In these cases, we always aim the cameras inward to shoot pictures from a single target. But Camera Array tool is also capable of producing environments, such as interiors, all kind of rooms or other 3D spaces. Then we change our thinking and point the cameras outward, and for that we need to use slightly different approach. In this video we focus on the object-centric method because it is the area where the biggest innovation of this version of the camera array tool lies, and where we are now able to create an animated 4D GS datasets. But before we can go into that, we need to know the basics. The camera array tool is a Blender add-on that appears in the N panel after installation. This means that with the shortcut key N, you can turn on the side panel on Blender's viewport, and there you can find the camera array tool's main panel. How the camera array tools works in practice is that it is used to create cameras on the surface of any mesh object. We first create basic primitives such as boxes, cylinders or spheres and use them as array rigs for multiple cameras. The basis how the camera creation works is that the script looks at how many polygons there are in the object. This can either be the quad polygons, which are basically these rectangular shaped faces, or basic triangular polygons. In either case, the center point is calculated from these faces and the camera is placed at this point. The camera will be created to aim in the direction of the surface normal, either inward, outward, or both directions if necessary. So as many face center point as you have in your array object, as many cameras will be created from these mesh faces. Blender's own icosphere primitive is a good basic object because it consists of 80 polygon faces. So using it as an array object creates a total of 80 cameras. As a new feature, I have now included this option to choose pre-made objects. From this drop-down menu, you can choose from 5 different ready-made array objects. I have designed this so that they are well-optimized primitives that produce only specific number of cameras, and each one of them is designed for slightly different purposes. Let's go through them briefly. For example, this half-dome pre-made object produces 60 cameras and is good basic object for rendering images of various figures and other object-centric models. The dynamic cylinder is an object that can be customized with parameters. If you use this, you can adjust its polygon count from its modifier settings here. There is also a pre-made object called interior tower. It is a very simple tower consists of 3 boxes that is designed to be used when we want to capture environments and create images of, for example, rooms or other interior spaces. In addition of this, we then have two of these minimum cam angle objects. I have carefully calculated that if we want to speed up the process and create only very small number of images, these simple objects can be used to create either only 26 or 17 cameras. The 26 version is used in cases when we want to capture our 3D object from every angle, including from below this imaginary floor level surface. But the minimum 17 is designed for cases where the angles below floor level are not important. For example, if we capture images of a car model and we know that we will not use the views from the bottom of the car, then it can be practical to use only 17 array cameras and render projects faster using only these optimized angles. In any case, the basic function works like this. When we have created any object and made sure it is active, we can press this Create Cameras button. The cameras will appear on the object surface in the direction that is selected in this menu. From the outliner list, we can see that all created cameras appear inside a collection called Camera Array. And their naming is done using the name of the original array object and with the method that was used, which is by default marked as in because we had used the inward setting here. Okay then, when we move the original array object, we see that all the cameras follow along and remain attached to the object face surfaces. So we can manipulate the shape of this rig very easily by scaling it in different axes, or we can switch to the edit mode and move individual polygons or polygon groups. And when we leave the edit mode, the camera array setup will update. So modifying all the cameras at the same time is very versatile and fast, simply just editing the original array object. Okay, now I'm going to start from scratch and quickly create some 3D model in here. I like to use this separate Blender kit library, where I can find a lot of usable 3D models that can be used as an example in here. From this library I bring this funny looking Santa Claus figure in Blender's scene origin point, and after that I use this pre-made half dome object. I scale it to go roughly around the figure and then create the cameras on its inner surface. When I turn the camera view on from this viewport button, I get the view of the active camera. I can now change the camera angles by clicking one of these cameras in the camera array collection. Activation is done by clicking this green camera icon. Since Blender is set up to use the 16:9 aspect ratio by default, I now want to change it and go to this output menu. I prefer to use square images, so I set the resolution here to 1080 by 1080. The camera array listens to Blender's basic settings, so if I want to change the image saving format, I can change it here. The same applies to the rendering settings. If you want to use the Cycles rendering engine, you can switch it to it from the rendering settings normally. However, I want to use Eevee rendering for now because it's faster. And while I am here, I will also make sure that the transparency settings under the film setting is turned on. This ensures that the images have no background and the 3D object is rendered as PNG image without the background color. Now we can align the cameras better. Here is the focal length control, which can be used to adjust the FOV values of all cameras at once. I set this roughly so that the 3D character being captured at each camera angle would be visible as a whole and would not be cut off from the edges of the images. Then we need to remember to set some lights into the scene. I usually use some HDRI background to get even light to the scene. But of course you can use all different lighting types from Blender's own collection as well. Then we define the output directory. Defining this path is important because this is where we will then produce all the images and later also other parts of the dataset. So it is a good idea to create a completely new folder for this project and make sure that this output path points to it. And now that everything is in place, we can start rendering the images by pressing the Render Cameras button. Before accepting the rendering, a small confirmation window pops up and tells you what you are doing. It shows you the number of the cameras and reminds you that the rendering process you are starting cannot be stopped. I need to say that I have been struggling with the Blender's rendering commands for a long time during the development phase, and unfortunately I have not been able to get the process stopped properly. So be aware of this and double check everything before you continue with the rendering. In this case, when we use Eevee rendering, the process is so fast that we don't have to worry about interrupting the process. We can follow the progress in the File Explorer window, where we can see how finished images appears one by one in the folder. My recommendation is to first do the test calculation using the faster Eevee rendering engine. When the images are as you wish, you can then move on using the heavier cycles rendering, because its process takes longer. Either way, when the images are ready in the folder, we have now performed the basic function of the camera array tool. These images can already be utilized in the Gaussian splatting calculation by dragging them into the Postshot program. However, it should be noted that the Postshot has to utilize the so-called structure from motion method and infer the camera angles again based on the data collected from the images. This is a heavy process and takes more time, and depending on how much the images you have produced, Postshot will either succeed the conversion or not. But for this, we can simplify the Gaussian conversion significantly and collect the camera data that we already have available in Blender and write it in the so-called call map format that the Postshot program will understand. So we can now expand this call map exporter section from the camera array tool panel to make those next steps. The call map data consists of 3 TXT files. These are the cameras, images, and points 3D TXT files. The first 2 of these are needed to store the camera information and 3D coordinates. And now that we have the rendered images, we can create these first call map files. In previous versions, these functions were separated in 2 separate buttons, but now in this new version the function is combined behind one button. When we click on it and check the directory from the File Explorer, we notice that now we have 2 TXT files there, cameras and images.txt. After this, we only need to generate the 3D point cloud. And it happens so that when we first select an object from the scene, which in this case is this Santa Claus figure, and then we just click this Generate Points 3D TXT button, we now get the last TXT file that we need in the same directory. And this is all we need to do to generate the call map data. The dataset is now ready, and when we drag all these images and these TXT files together into the Postshot program, which by the way is more easier if we drag the whole folder in there, we can start the Gaussian splatting training right away, and we don't need to progress any time-consuming structure from motion phases anymore. However, I still want to look at the point cloud file a little more closely. When we look at the points 3D TXT file, we notice that its file size is quite large compared to other TXT files. This is natural because point clouds can be large, and it holds 3D spatial information about each of its points. The way the point cloud is created in these cases is that in Blender each vertex point of the 3D model is written as a part of the point cloud. If the mesh structure of the model is very dense, This means that there are very large number of vertex points. So in some cases, the size of the point cloud file can grow to several tens of megabytes, and then writing and saving the points3d.txt file also takes more time. If we want to optimize this and produce only very few points, I have developed a density slider for this. This allows you to adjust how many vertex points from the model are written. If it is set to 100, like it is by default, all points are included and the point cloud will be also the largest. If you reduce the density value, the file size will decrease. In the Gaussian splatting process, the density of the point cloud affects slightly in the processing speed how fast and accurately the Gaussians will find their places in 3D space. But what is even more important is that now the camera array tool can produce colored point clouds. This color point setting is on by default, and it means that now colored points can be created from the Blender based on the 3D model's textures or materials base color values. This helps and speeds up the Gaussian splatting process in the Postshot considerably. Previously, I was able to generate only white points, and even that produced a working Gaussian model, the formation of the splats took a little more time, and the training was done in an interesting pulse-like formation sequences. Now the colored points helps the Gaussian find their places in the 3D space much faster, and the construction is going to be whole already in very low iteration steps. So colored point clouds are definitely a good innovation in the camera array tool, since it makes the final Gaussian training faster. Now it is time to move on to the biggest part of the update, which is this bottom section called Animated 4D GS Data. This makes it possible to generate datasets from animated objects. Here I have this funny looking wrestler character that I have imported here in Blender from the famous Mixamo character library. I see that this character has this walk cycle animation which seems to be 25 frames long. So I changed this end frame value to 25 to match that loop and check out how the walk animation look like when it's played. If you have longer animations or if you just need to use only part from your longer clip, Camera Array tool will listen to basic settings of the animation frames. You can set the start and end frames from the Blender's output panel, and if you like to render only every second or third frames from your animation, this step frame value work also. Then I choose this pre-made minimum cam angle 17 object and create array cameras from it. I'll check that the composition of each camera looks nice and that the character is in the middle of each camera view. Then from the 4D GS section, I'll choose this character body to be my animated object. Since this character is formed from only one mesh object, this is easy to produce for animated point cloud. If you have some other type of character or animated object which has several different items on it, like separate cloth pieces, I recommend that you use Blender's own join feature to put them together and then choose that to be the animated object in here so that it will cover most of your character's features. And then when I'm ready and this include coal map data is checked on, I can start rendering the animated frames. Again, this small attention window will pop up and tell you how many cameras of each of these frames you are going to render with these settings. If everything seems to be fine, we can start the animation rendering. The steps how the animation rendering proceeds goes like this. First, it will render only the images, and it will make separate folders for each animation frames. So in this case, we are going to have a total of 25 frame folders where each 17 camera array images will be rendered. Then, after the image rendering is ready, the call map processing starts, and the script will go through again all the folders and put the call map data inside each one of them. Only after this, the animated 4D GS data is ready for further processing. Okay, good job so far. Now we have gone through all the key features of this add-on, and basically everything we can do with the camera array tool is now done. Where we continue from here and where we further process the data is entirely up to other separate programs. But of course we want to finish this 4D GS animation, and that is why I will also include in this video the next steps that we need to do in the Postshot program.
Activate.
So, the idea how 4D GS works is that we need basically train Gaussian splatting file sequences. And these numbered files can be either in splat.py file format, or second option is to save the sequence in Postshot own native format, which is this .psht. Actually, one way we can do this is process each of these frames manually by dragging them in Postshot and drain them one by one into these Gaussian splatting formats. But that is of course very tedious and time-consuming job. And what can save us from this laborious phase is the option where we use a version of Postshot that works via the command line. This Postshot CLI version comes with the Postshot installation, which allows you to train Gaussian models from the command prompt. But don't worry, I'm not going to make you type in all these complicated commands and parameters. I have developed a script that will handle these commands for you. This software of mine is called Postshot Batch Trainer, and its latest version 2, I have taken better account of what is needed to automatically train all these frame folders. But before we can go any further, I recommend that you check out and update your Postshot installation to be the latest build. Postshot developer have just made a new great update for the program, and now the CLI is more stable and runs better. You will find all the necessary links in the description below. I am using this Postshot version 0.5.79. After you have installed these programs and launched the Batch Trainer, you will see a small application window like this, and it opens with a terminal window from which we can later monitor the progress of the training in more detail. Batch Trainer is designed to be very simple to use. You just need to open the location of your dataset directory by clicking this input folder icon. Then you need to navigate to the path where you generated all the numbered frame folders with the camera array tool. Trainer will tell you in the bottom status line how many numbered folders it finds in the input location. Then we define the output path where we want to save all the trained Gaussian splatting files. I'll usually use the same location as the input folder because I want all the files related to this project to be in the same place. But you can save these sequences wherever you like. Then I can give these files a prefix name and also decide how many iteration k steps I'll let the trainer go with the Gaussian models. This basically means the accuracy of the model. I put 5 in there since I want this process to be reasonably fast. And since we use the call map data with the colored point cloud, we now know that the model will be complete even in very low iteration steps. After this, I'll choose the profile setting. When we are making synthetic Gaussian models with these pre-rendered images, the ADC profile has turned out to be the best choice. It makes better quality and smaller file size than the MCMC. After this, we choose in which format we want to save these files. PSHT is the Postshot own format, and the PLY is more convenient universal format, which can be used in other platforms as well. And then, when all these minor options are set, we can start by pressing this Generate Sequences button. In the terminal window, we can see how the Postshot CLI version is running the training process, and also in the Batch Trainer we can see the feedback from these growing progress bars and status info, which tells you how many of the frame folders have been done. This will take a while, so take a cup of coffee or something while it's working. During the batch run, you can also watch the output folder and see how the complete files will drop in there one by one as the trainer finished them. If for some reason the Postshot CLI trainer will freeze suddenly during the process, you can press the Generate Sequences button again. This will check how far you have managed to build these files, and it will continue from there. So you don't need to start the whole process from the beginning. But if everything goes well, like it now should, you will eventually receive a message that the entire training process has been completed successfully. After this, you can close the Batch Trainer window and the terminal. And finally, now we are ready to check out what our 4D Gaussian Splatting animation turned out like. This is done simply by dragging all the created PLY files, or if you made PSHD files, here to the empty base in the Postshot window. The Gaussian model will appear there after a short while, and you can watch the animation itself when you drag this cue pointer from the timeline. Since our animation was 25 frames long, I will type it here as the last end frame value. And now you can press the play button from here in the middle. The animation will loop and we can see it from all sides. We have a few options to influence the display speed by changing the FPS values. This happens when we activate this scene folder here at the top of the hierarchy list. From the parameters that can be found below it, there is frame rate setting, where you can choose from these standard 24, 30 or even faster 60 or 120 FPS values. Well, this is the 4D GS playback that Postshot is currently capable of. A similar function can also be found in PlayCanva's SuperSplat web program, and if you trained the PLY sequences, you can drag those same files in there. SuperSplat allows you to play the animation and set the FPS settings to slower speeds, such as 12 frames per second. So this is the overall workflow for creating synthetic 4D GS animations. Since this is quite new, there are not many applications available yet where this animation could be used. But I believe that very soon we will be able to load these Gaussian animation that we have produced ourselves into virtual reality environments or other augmented reality applications. However, in Postshot you can already play a little bit by blending animation in different environments. Since you can now import multiple radiance fields into the Postshot, you can combine them and import a static environment in the background of your 4D GS file. Alright, I want to thank you for watching this video this far. There was a lot to cover. The camera array tool update is available in my Gumroad store. If you have already purchased the previous version, you will receive this update for free. As I said, all the important links can be found in the description below. I hope you like this Blender add-on, and if you decide to purchase this, I will be very grateful, as it will support my research and development and making of these videos. Leave a comment with your thoughts, and if you like this video, press the like button and don't forget to subscribe to my channel. I wish you all happy arraying. Goodbye.
Activate.